We'll take a close look at L'Hopital's rule, which is a great tool for evaluating certain limits. It's usually used for distinguishing indeterminate forms, and of course, if you could distinguish indeterminate forms, you're going to need to be able to distinguish determinate forms as well. We're going to use algebra and L'Hopital's rule to calculate limits of specific indeterminate forms. You're going to gain the intuition on functions that grow faster than other functions. And of course, we're going to revisit and use limit notation appropriately so that you understand that you always have to be 2 steps ahead when you're trying to evaluate limits. Now, there's actually 2 cases for L'Hopital's rule. There's the first indeterminate form of 0 over 0, but it's really not 0 over 0 because remember, when you're looking at limits or when you're trying to check forms of limits, you're trying to see if it gets close to 0. So if it gets close to 0, it's really representing the concept of very small over very small. So L'Hopital's rule says this: if f and g are differentiable on an open interval I, which contains a, with the denominator not equal to 0, and if you look at the form of the numerator and the form of the denominator, and they both get close to 0, then L'Hopital's rule says you could try to simplify this limit by analyzing the derivative of the numerator over the derivative of the denominator, and then try to take the limit. The rule may also apply for cases of infinity or negative infinity, and you could certainly let x approach a from the right hand side, or you could let x approach a from the left hand side. The second case for L'Hopital's rule has to do with these indeterminate forms. Remember, infinity is not a number, so whenever you see the concept of infinity, think of the phrase very large. So these forms are basically all very large over very large. And it doesn't matter if it's very large in a negative direction. Once again, L'Hopital's rule says, if you check the form of the fraction, and the numerator is approaching infinity, and the denominator is approaching infinity, then L'Hopital's rule says you can now analyze the limit by taking the derivative of the numerator over the derivative of the denominator, and then try to take its limit. Once again, the rule applies for infinities, or as x approaches a from the right or from the left. Some special remarks about L'Hopital's rule. First off, L'Hopital's rule is not related to the quotient rule of derivatives. You have a separate rule for that. In fact, the quotient rule has nothing to do with taking limits. So treat L'Hopital's rule as a tool for evaluating certain limits. You got to remember, infinity is not a number, but represents the concept of very large. Another thing you want to keep in mind is that L'Hopital's rule does not always work. It's a very powerful technique, but it's just one of your many techniques relating to algebra. Other techniques relating to algebra are needed. Throughout the upcoming examples, we will analyze some other indeterminate forms, and there's quite a few of them. The first one here says very close to 1 raised to very large. It's very hard to imagine that or picture that. What does that mean? This is even harder to imagine. What's very small raised to very small? Another one that is indeterminate is very large raised to very small. This one's more intuitive. I mean, if you think about very large, subtract very large, that doesn't say much. Just imagine 1 trillion minus 1 billion. What's the outcome? Here's another one that's hard to understand. What's very small times very large? Now, these forms are extremely vague, and that's another reason why we call them indeterminate forms. You simply cannot conclude much when you have these forms. And notice very small times very large in the negative direction is also an indeterminate form. Why don't we go ahead and get started and use this powerful tool to evaluate some of these limits. So remember, when you're trying to evaluate limits, you have to be 2 steps ahead anyway. L'Hopital's rule just says you got to be a step ahead in the numerator and you have to be a step ahead in the denominator. Remember that the tangent of 0 is actually 0, so this fraction here has the form of 0 over 0. And that is because the sign of 0 is actually 0. Now remember, x is approaching 0, so instead of saying 0 over 0, just try to say the phrase very small over very small. That is indeterminate. But because we have a fraction, L'Hopital's rule, which I will symbolize with an H, says we could analyze the limit by taking the derivative of the numerator and the denominator. So using the chain rule, we get this. And we also need the chain rule in the denominator. We get this. And now we check its form. If you check its form, remember that the secant evaluated at 0 is just 1, and the cosine evaluated at 0 is just 1. So if you check its form, notice you are 2 steps ahead. This is approaching or getting very close to 6 over 2. This is a determinate form, okay? So this is not one of those forms in the list of indeterminate forms. 6 over 2 is a determinate form, and that means you could actually write limit laws. You know, you're 2 steps ahead anyway. So why don't we do that? We can go ahead and write a limit law because you know the limits do exist. This is the only time you could actually write a limit law is by knowing that the limit of the numerator exists and the limit of the denominator exists. And notice you indeed get what? You can evaluate now, which is 6 over 2, and you no longer have to write the LIM notation. That's pretty cool. And you can see how powerful L'Hopital's rule can be depending on the scenario. Here's another limit, another expression. Once again, we check its form. This looks like 0 times 1 in the numerator. So this is getting very close to 0 over 1 minus 1 in the denominator. So this is also getting very close to 0. Once again, we have very small over very small, which is indeterminate. We're ready to go ahead and use L'Hopital's rule. And we need a derivative of the numerator, which is a product rule. And we need the derivative of the denominator, which is simply this. We could check its form again, and notice when you check the form this time, you get something really cool in the denominator. You actually get ln of 7. It's getting very close to ln of 7, and the numerator is just going to where? Let's see. It's going to 1. And what's 1 over ln of 7? Well, that is finite, and that is a determinate form. That means you're 2 steps ahead. If the limits do exist, you could write limit laws. And notice, since this is going to exist, you can go ahead and take the limit now. And we just have a 1 in the numerator. And once again, this is the powerful or the power of L'Hopital's rule.